So now our next speaker, Angela de Palma-Dow, will talk about the implications for managing wildfire and climate change impacts on long-term phosphorus in a large, shallow, hypereutrophic lake.
Here you go. It's a mouthful. Thank you. Thank you. Round of applause. Alicia's very awesome to work with, and I love working with Davis' team. And everybody got a seat. I want to make sure. Yeah, okay, everybody's scoot over. Okay, great. So I want to thank the co-authors. Michigan State University in McCullough is in Houston. They did work for this under NSF grant, so they put in their time at no cost to the Watershed Protection District and County Water Resources. So I'm grateful to them. And Jennifer Redbert from University of Vermont. And this is a map of wildfires in Lake County from 2015 to 2020. It seemed like every year we were getting one or two wildfires. Over 55% has burned within that 5-year period. The largest one is the Mendocino Complex. You guys can see there in red. And then we all know that Lake County is a disadvantaged community. However, 60% of drinking water comes from Clear Lake. And this is, within the basin where that drinking water came from, there was over 40% of that watershed was burned over those 5 years. And when we're trying to recover from a fire, there's another fire. And so recovery efforts and being able to monitor what's the impact of a single fire is really difficult because you're dealing with yet another fire and impacts from that. But we do know that there is a need for post-fire studies, particularly in lakes. So we have, data from many years about fires around lake systems, but most of these lake systems are in heavily forested boreal regions. So that's, think of upper Midwest, Canada, really forest, not like Clear Lake Mediterranean ecosystems. And then freshwater impacts on fire is also lacking. So there was a need to do more research on wildfire impacts in lakes. And Clear Lake is unique. We don't get ice cover. A lot of these lakes up in the northern latitudes have ice cover, so they act very differently. They're cold, they're deep, they're not as nutrient productive, they're not as shallow. Alicia was talking about depth, so we're at 27 mean depth here in Clear Lake. Our lake is really old. A lot of those lakes where fire research has been focused on in the Midwest, those are all glaciation lakes, so they're only about 20,000 years old. Our lake is 500,000 years old in its current shape, so very different. And then we are very productive, and we do have a TMDL, and that's a fancy acronym for saying that we're supposed to manage our sediment phosphorus that goes into our lake because it is an impaired water body. And I really want to stress how unique Clear Lake is. So we use data from the Lake Lagos macro scale study. So we're looking at lakes across the country, and you have the 3 different colors. If they're blue, they're oligotrophic. That means low productivity, like Lake Tahoe. Eutrophic is a little higher productivity, like Clear Lake sometimes the year, and then hypereutrophic in red is super productive on steroids. So you guys can see where the hypereutrophic lakes are in the country and where Clear Lake is right here in California. And so just know that, there's not many other hypereutrophic lakes out there in the Western region. So when I say Clear Lake is unique, I really mean it. And here's the data to back that up. And then further, our lake is unique because we have 3 basins. And each of those basins kind of acts a little differently, and we can't group everything into one. We can't go and take one sample in the middle of our lake and say, well, there we go, we've captured it. And you saw in Alicia's talk where she had data all split up into 3 basins. And so if we look at Clear Lake, CL1, that's the upper arm, CL4 is the Oaks arm, and CL3 is the lower arm. You guys can see where they fit on this dot. The blue dots are the light blue dots are ligotrophic, eutrophic lakes are a little more productive, and then hypereutrophic are the purple. And the first chart we have there is how big lakes are and their chlorophyll. So how much green productivity, green algae is out there. And you guys can see where Clear Lake is all on this side. So for our size of our lake, we're really productive compared to many of the other lakes in the US. The middle chart shows you the watershed area. So a little more in the cluster. And then the third chart on the right is the ratio. So a little more definitely in the cluster there, but still unique tendencies for Clear Lake. And this one shows just in comparison to California lakes. So looking out in the west. And again, we're kind of off the charts and compared to other lakes in California. On the left there is the lake area for how big our lake is. for average chlorophyll, which is green algae productivity. And the middle chart is our watershed area. And then we're a little closer for the ratio of how big our watershed is to our lake size. So again, just to hound in how unique Clear Lake is, and why we really need studies specific on our type of lakes that has to do with fire impacts. So these are some of the research questions we're going to go through here for this talk, with the first one being, what is wildfire occurrence in the watershed? And I showed you a blip of a map for the 5-year period, but we have more information over time for that. And this is the data sets that we used for this project. And we really focused, when we looked at nutrients and impacts in the lake, we looked on phosphorus specifically, and we looked at a time period with the blooming month. So we all know what that means if you live here, right? Between July and October, our lake looks a lot different than it does the rest of the year, because we have those big blooms in certain parts of the lake. You get a lot of smells and coloration. And so we really wanted to look at phosphorus within those time periods. And we also know that phosphorus is one of the drivers for cyanobacteria blooms in the lake. And it is the focus of a lot of management regulatory processes. And I work for a regulatory county, so we have to consider the management components of this. So this is the wildfires that occurred in the Clear Lake Basin since 1923. And then we have the graph on the right is just showing you the size of those wildfires and over time. And we really only have water quality data from about 1968 for nutrients. So if you look at the way fires have changed, the size over time, we really only have 3 big fires in the basin that we can look at with water quality. And when we look at severity of burn impacts and watershed size, like, that data is really skewed and hard to work with, so it was a reliable way for us to look at impacts of wildfire. But what we can do is pick out those 3 wildfires, and we can look at, say, nutrient data from before and after those fires, and kind of compare and see what is going on. And when we look at the way that fire data collection has changed over time, on the left-hand side is the burn severity. This is the Mendocino complex. So what on the landscape burned really hot and what didn't burn really hot. And we didn't really have that data for a lot of the other fires early on in this data set. So we couldn't look at the area of burn severity for these fires in this analysis. But it just gives you a little idea of where those fires were located. And these are the locations. Again, we have to sample all 3 arms because each arm is different, has its own personality, and we need to capture that information. And this data was collected by the California Department of Water Resources from 68 until 2020. And then the Lake County Water Resource Department took that program over in 2020. And so what we have here is the upper arm is going to be on your left, lower arm in the middle, Oak's arm on the right. And this is the amount of phosphorus that we see in the lake pre-fire, which is blue, and post-fire, which is red. And so we looked at the last 3 fires we had. 81 is at the top, 96 is in the middle, and then the Mendocino complex on the bottom. And this was all surface TP, or total phosphorus, because that's where the blooms are. We looked at 3-year pre-post. There was missing data in 2020, and we really didn't see any increases in phosphorus in the after of fires. In fact, we saw some decreases in phosphorus after these fire periods. So that was really interesting. This is limited data, and we looked at 3 years because USGS defines post-fire recovery in a window of 3 to 5 years. And so we kind of wanted to get into that window there. But after 5 years, guess what? Either there's a drought or a flood or something else in that timeline that kind of made us uncomfortable with looking at that 5-year stretch of data. And this is kind of limited, but this is more data than a lot of water bodies have. They do not have pre-monitoring data to match with post-monitoring data, let alone for multiple fires and in eutrophic lakes. Like, it's a data set that really doesn't exist out there. So it's really important to have and put out there into the literature. There's other things to consider. I'm just talking about phosphorus, but after a fire, there is lots of carbon input. So all that burned ash material runs off the landscape and goes into the lake. And because we are a drinking water source, there's a lot of treatment activity on the lake. So 17 water purveyors out there are taking in water and they're treating it. It's very expensive to treat that because there's so much rich stuff in our lake. And there is some issues with long-term ash accumulation, burn sediments. they interact with some of these treatment products, and they can have long-term cancer-causing properties. So it's really important that we continue the study of post-fire impacts, especially in a lake like Clear Lake. And I just wanted to acknowledge that even though my study wasn't focused on these other nutrients, that it's a investigation that's worthwhile, particularly for drinking water purveyors. And this graph from our partners at Washington State University, those blips indicate the pulses of carbon post-fire events. So our second research question, well, if wildfires aren't contributing really to phosphorus in the lake, maybe there's some other trends. Maybe it's climate related. But let's look and see, are phosphorus concentrations even increasing? And so again, you just wanted to look at those bloom periods, July through October, some of the medians, and we have the upper arm on the top, lower arm, Oak's arm, and along this x-axis, you have the year. So from 1968 all the way to 2021. And then phosphorus concentration in milligrams per liter on the y-axis. And yes, we do see increases over time. So typically after 1988-5, you guys see that? Things look a little different after 1985? Okay. Crazy time in the 80s. So wildfire not really contributing to phosphorus. So what's going on? Internal loading, we have talks about that. And so that, we wanted to look at overtime relationships between oxygen and phosphorus. Now, this data is once a month, 10 times a year. So it is coarse, but it is a long-term data set. It does not going to give you that resolution that Alitia's project, Mika's project we're talking about, where they did sampling, continuous sampling. This is over time, once a month. And we do have delineated on here the hypoxic or low oxygen periods, the anoxic periods in there. And we do see that we have periods where we go below over time into those categories. And do we expect it to occur over time? We looked at the numbers, like just raw numbers, and we didn't really see a difference with that over time, just based on the selection of data that we looked at. But what we did see was when we look at, so the phosphorus that's in the lake that's the most available for organisms like cyanobacteria is soluble reactive phosphorus, and that's called SRP. And we're really lucky that we have that long-term data set. And we wanted to see if that was related to low dissolved oxygen. So Alicia set this up great. She talked about the relationships between SRP, low oxygen in the water. And so over time, we are seeing that relationship. We're having low oxygen. You also see, you see increases in the most available phosphorus when you have low oxygen in the water. That's why you have kind of that negative trend in each of those arms there. And when you look at the same depth for the hypoxic conditions, so that's less than the 2 milligrams of per liter oxygen for just phosphorus, total phosphorus, you don't really see too much of that same relationship. It's really that phosphorus, that reactive phosphorus that's there that we're seeing. So the last thing, or one of the last things we looked at was maybe there's some climate variables going on here. And so we looked at minimum maximum temperature, precipitation. This is a recent photo of Clear Lake during the drought. We all recognize that. And we did see that when we looked at some correlations. So the most strongest predictor for our phosphorus in over time, those increases, was warm winter and summer maximum temperatures. Precipitation. So less precipitation in the wintertime led to more phosphorus in the water column. And thus that's an indicator of drought when you have less rain. And then I wanted to kind of look at that. So we looked at what the state defines as significant drought period. So the years where there's significant drought, multiple years in a row, is where we see the majority of these increases in phosphorus over time. So I didn't do a statistical analysis on this, but I just looked, just wanted to see if there was a pattern. And we kind of see that when there's less water coming into the system, slightly warmer temperatures, we do see increases of phosphorus in the lake. And then when we wanted to look at temperatures, because we kind of looked at dissolved oxygen, we want to see maybe there's some relationship with temperatures over time. For that time period, we didn't still really see significance in all the arms at the surface. But when we looked at just that chunk of 1985, when we started seeing increases of phosphorus, we definitely saw temperatures are warming. And then we look at the deep water, they are warming the whole time period, and all of them over that 1985, same thing. So what this tells us is the lake is warming throughout the surface and the bottom over time. And there's something about that period since 1985 that's interesting for nutrients in the lake and temperature. And so this is not uncommon, and this is actually something that's occurring globally. And so we're seeing these changes in processes at a global scale all around this time period. So is Clear Lake susceptible to these global climate shifts? Absolutely, I would say so. And, we definitely need to consider that when we're managing the lake, and then when we're going forward with other research. So some of the take-home messages for that, as a manager, it's really important for us to understand what's going on with the lake. Let's say we put $1 million into, post-wildfire phosphorus control. Is that a good use of our money? As for the taxpayers' dollars? Probably not. And so we needed to do this research to be able to figure that out. And so that, is really helpful for us going forward, especially when we're having these wildfires in the basin. And I kind of attribute it to, there's so much good stuff in the lake already. It's so productive that these single large event episodic wildfire events probably aren't adding much more nutrients into there when it comes to phosphorus. It's like a really sweet cheesecake. You add a little more sugar, it's still sweet. Tastes the same thing for Clear Lake and wildfires. But the legacy of Clear Lake makes it really hard to isolate those impacts because there's so much going on. It's such a complex and unique system. And we really don't have any other studies that are comparable. There's not other lakes like Clear Lake out there that have done work like this that we can look to as a model. And that also means management. So that's why we have symposiums like this and the researchers, and we're thinking of all these technologies because there's not other examples out there that are as unique as Clear Lake. And it's really important for us to continue looking at these large-scale collaborative studies. And we also have to remember that this is a drinking water source. And so there's sometimes things that drinking water treatments need a little different than, say, agency that are looking at just other water quality metrics. And then the moral of this probably will be continue monitoring. We have this great long-term data set. And it stopped being funded in 2020 by the state, California Department of DWR. The county was able to take it up, but we're doing it bare bones, abbreviated. There's a lot of things they were monitoring that we're just not able to do because we don't have the state lab capabilities they do. And we're really thankful for the Blue Ribbon Committee and other sources to keep that funding going, but it's not sustainable. And if we want to keep monitoring in the lake, we have to find funding sources for that, so we can keep producing studies like this. And I thank you for your time, and I'll take one question. Yes.
Angela, great talk.
Thank you.
And I guess I'm not as, I shouldn't be as surprised, but maybe I am surprised that we didn't see an increase in phosphorus with the fires. The fires, don't contribute just phosphorus, or may not contribute just phosphorus. There's a lot of silica in the retardants that are used. Do you have any indication of how much silica is in the lake? And because that will shift, obviously, the edited advantage for things like diatoms as opposed to silence. And I wonder if you had any insight on that.
Yeah, the question was if there's any increase in other things, particularly like silica, which is important for diatoms and phytoplankton and cyanobacteria that's in the lake. We have that data set, and we have been analyzing it. So far, no other nutrients are really popping out post-fire. I am working on it with researchers from Michigan State. They're doing it pro bono, so when we have time, we're looking at it. But yeah, so far, nothing else really is coming out strong, but we're still working on it. So I'm hoping to have that presentation over the next few years with that. But yeah, we did do an effort to look at silica after, and we include it when we do stream monitoring after a fire in the first flush, to kind of see what's that impact that's coming down the streams after a fire. When we did it after Mendocino Complex, we didn't see it come out. We saw things like iron, manganese, aluminum. I think Sarah, she saw it after the, did you guys sample it for the Rocky Fire or Valley Fire? You guys sampled it. Did it pop out? I think you had aluminum pop out. Silica popped out. Yeah. So it's something that we're looking for now that we do post-fire studies in the streams. But again, we're limited because those funds are like minimal. Yeah. Okay. Thank you.
It's so counterintuitive. You would think that the phosphorus would increase. Perhaps it's because the fungi in soil, mycelium, which etches phosphorus from small particles, takes it to the plants. Perhaps since that's killing hot fires, that may be causing the decrease in phosphorus. Have you considered that?
I have not. We just looked at the lake, inside the lake, but yeah, that's something we don't really, yeah. We're not sure.
Because otherwise it's very costly. Why would it increase? Because the soils disturbed, you think it would be small.
I will say that I personally think there's some patterns with drought periods and flood periods. And I think some of these periods post-fire we're inundated with floods. And so dilution is a solution, right? You're getting a huge influx of fresh water. And so you're really kind of seeing these flush out of some phosphorus. I think in these cycles that we've seen where we have a couple of years of drought, a wildfire, a flood or a couple years of flood, like personally, that's what for the most recent, 20, 30 years, that's what I think is happening. But it needs to be explored a little bit more. Yeah.
Yes, absolutely. It's great.
We see during high water years, less phosphorus in the water column, actually. Yeah. I'm going to have Charlie come up and Elisa, but do you want me to answer one more question?
Getting off that. Yeah. So without the pilot, obviously the runoff from activated charcoal, what about the creation of possibility without? So that's it makes it.
Yeah. So there's things with that, but you're talking about like getting the burnt materials activated charcoal. But on firm slopes, the stability of that is really precarious and you actually will disturb. And what you want is plants will come back right away in that disturbed soil. And so you want to be able to let them have that chance on the landscape to do that. And then the county is doing another study with biochar that's produced, that's controlled, because not all biochar is the same. Yeah.
What I was getting to was with the runoff, the first flood,
right.
Some of that sediment coming down into the lakes, and you have more activated charcoal actually into the water.
Oh, you're saying it's filtering out the phosphorus in hand.
Potentially by the and then in the aquarium with carbon.
Yeah. So what we have to do is attach it and sequester it and keep it out of the water column, because when we're, the sampling is between July and October. So it's a good post-fire. Like, yeah.